Right. Welcome everyone to another installment of TCS Plus. Today we're happy to have Michal Feldman from Tel-Aviv University, who's one of the world leaders in algorithmic game theory. And today she's going to tell us about an exciting new area in this broader area called algorithmic contract theory. You might remember there was a talk about this by Baltan Gam Cohen last semester, so Michal is going to give us her take on this. We were so excited we wanted to hear more about it. Before I hand over the mic to Michal, let me add a few quick words, starting with a quick shout out to all the other organizers of TCS Plus, Clément Canon, Rachel Cummings, Anin Yadeh, Sumay Agag, Gautam Kamath, Ilya Rosenstein, Oded Regev, Sidu Shram, Noah Stevens-Davidovich, Thomas Vidik, and Eric Weingart. Okay, got all that out of the way. Before we start with today's exciting talk, I'll also add a little bit of advertisement for the next talk in 2 weeks, where Scott Aronson from UT Austin will tell us about connection between quantum supremacy and randomness. But that's 2 weeks from now, and with that, we can start the proceedings. Michal, please take it
away. Thanks, David. Thanks to the amazing group that David mentioned for organizing TCS Plus. It's a pleasure to be here, and thank you for everyone who is here. So indeed, I'm going to talk about a relatively new area called algorithmic contract design, and today's talk I'll focus on combinatorial contracts, and I'll tell you all about it later. I'm not going to assume any prior knowledge on contracts. Let me just mention that this is based on 2 papers. One is very recent. It will be presented in Stock 23, and the previous one was presented in Fox 21, and this is all joint work with Tomer Ezra, who used to be my PhD student. He's now doing a postdoc in Rome, and he's soon going to start his next postdoc at Harvard. Look for him, you want to work with him. And also Paul Dutting and Thomas Kesselheim. Great. So you may know already by now that algorithms interact with strategic agents in many ways. And this observation is by no means new. We have algorithmic mechanism design, which is quite old already, and it captures the problem of hidden preferences, where the goal is to construct mechanisms that incentivize agents to reveal their private information truthfully. And today I'm going to talk about another way in which algorithms interact with incentives, and this is through algorithmic contract design, which captures the problem of hidden actions of agents. And the goal here is to construct mechanisms that incentivize agents to exert effort on behalf of the principal. Now, the nice thing about these 2 areas that are seemingly very different is that we can use a lot of the tools that were built for us, the beautiful playground that was built for us by a previous work, groundbreaking work on algorithmic mechanism design by Nissan and Ronen, and by Lehman, Nissan, etc. So we have the ladder of hierarchy of valuations, and we have different oracle models using value, such as value oracle and demand oracle. And this is all the playground of algorithmic mechanism design. And as you'll see soon, we are going to talk about algorithmic contract design within the same playground, using the same tools and terminology that was introduced for algorithmic mechanism design. So algorithmic contract design is a relatively new area, as I said, and it's part of an emerging frontier in algorithmic game theory, roughly speaking, on optimizing the effort of others. It's currently building a nice momentum with 2 recent workshops, both in Stock 22 and in EC 22, many recent papers. And those papers vary in their focus. So some are about combinatorial contracts, for example, contracts with multiple agents or with multiple actions or with multiple outcomes. So different papers treat different components of this complexity that arises. Other areas that belong to this emerging field are optimal scoring rules, delegation, strategic classification. So we are seeing many works that deal with this problem of optimizing the effort of others. Contract design, of course, is not new. It's one of the pillars of microeconomic theory, and it has been recognized with the Nobel Prize in 2016 to Holmstrom and Hart for their groundbreaking work on designing contracts. We can say that contract design plays a similar role for markets for services, like mechanism design plays for markets for goods. So algorithmic mechanism design by now is very well established. It's all about markets for goods. But nowadays, we have many online markets for services, including freelance services, legal services, marketing services, with applications like Fiverr and Mechanical Turk and many others. And as computer scientists, we know that as markets for services move online, they grow in scale and complexity. And so an algorithmic approach or computational approach is both timely and relevant. And traditionally, we know from algorithmic mechanism design that the algorithmic lens, when we apply the algorithmic lens to economic problems, it's very useful, for example, in revealing structure that can only be revealed using the algorithmic lens. So even though many problems were studied by economists for many years, some structure can only be revealed when we apply the algorithmic lens to it. We have many examples in mechanism design, and we'll see today some examples in contract design. The algorithmic lens is also useful in identifying tractability frontier, and then hopefully it can inform the design of simple mechanisms that work well in practice. So today, I am going to study the problem of contract design, applying to it the computational and algorithmic perspective. So let me start with the model that lies at the heart of contract design. This is often called the principal agent model. And at the heart of this model, there are two players, the principal and the agent. The agent works towards some task, and the principal is the one that enjoys the fruits of this task. So maybe we can think about the principal, who is maybe Rachel, and the agent, who maybe is David. And the principal wants the agent to maybe, for example, organize some event for her, maybe TCS Plus, for example. So she goes to David and she says, would you please organize TCS Plus for me? And David says, well, organizing this event is a lot of work. Like, I'll need to talk with speakers, manage the schedule, meet them 5 minutes before the talk, do logistic. It's very costly for me. So the natural question for David is to ask, how much would you pay me? And now, okay, so now Rachel thinks to herself, well, Rachel is not going to be able to monitor David's actions. She doesn't know if he really works toward getting a really successful TCS Plus, or maybe he just goes to the beach, who knows? The only thing she can monitor is the final outcome, whether the event was successful or not. And because she can't really monitor his actions, only his outcome, she can only base the contract, meaning pay to David, on the basis of the success of the event. So maybe Rachel tells David, I'll only pay you if the event turns out to be a huge success. Okay, so this is the principal agent model. Now let's try to get a more formal model out of this story. So we have a principal, we have two players, the principal and the agent. The agent can choose an action. For now, let's just say a single action from a set of actions. Choosing some action incurs cost, of course. Actions are not free, they are costly, and every action is associated with some cost, C of A. The principal is the one who is getting the reward from the action. So let's say we have some function f of A that says what's the probability of success given the action A. So every action has some probability of success. And it's the principal who gets a reward of, let's normalize it to 1, with probability f of A. So up to this point, of course, the agent has no incentive to work. The agent incurs the cost, and the principal is the one who enjoys the fruits of this costly action. So now comes the contract. The principal defines a construct, which is, in this simple case, nothing but some scalar alpha between 0 and 1, with the following interpretation. A contract alpha means that the principal pays the agent alpha in the case of a successful event. So the expected payment is alpha times f of A. And that's what the agent receives, okay? So what's the expected utility of our two players here? The expected utility of the principal is 1 minus alpha times f of A, because in the case of a successful event, the principal gets a reward of 1, and she pays alpha. Out of this 1, she pays alpha to the agent. What's the utility of the agent? The expected utility of the agent is alpha times f of A. So in the event of a successful event, she gets alpha, but she incurs the cost of her action anyways, independent of whether the project is successful or not, because she worked and she incurs the cost. Good. So this is the entire model. The defining features of this model are, first of all, hidden action, the action, and this is really important. This is called sometimes the principal agent problem, sometimes the hidden action model. The action of the agent is hidden from the principal, so the principal can only make the payment contingent on the outcome, which is stochastic. So in our case, the project succeeds with probability f of A. And another important feature of this model is limited liability, meaning that payments go only from the principal to the agent. The payments go from the principal to the agent, and they are non-negative. The principal can never get money from the agent. Okay, we're good. Any questions about the model?
Michal, you're assuming knowledge of this probability distribution mapping actions to reward?
Yes, yes. F is known and C is known. Everything is known, but the action taken by the agent. And the outcome is also visible.
So
yes.
Principal also knows C.
Sorry, can you repeat the question?
Will the principal also know the cost function C?
Yeah.
Okay.
Everything is common knowledge.
Okay.
There is no private information. There is only private actions.
Okay, thank you.
I have a question.
Sure.
One more question. So if you go back to the previous slide, if the function f is known to the principal, if c is known to the principal, assuming that the agent maximizes their utility, couldn't the principal calculate the best action? So the action would also be known to the principal?
Okay, good. So putting aside, we'll soon get to computational issues when we go to the more complicated model, but the principal indeed, for a given alpha, the principal can calculate what the action that maximizes the agent's utility. So, yes. Good. But the principal's problem is to find alpha that maximizes her utility, given that the agent is going to take the action that maximizes his utility given alpha. So you can think about it as a two-stage optimization problem.
Right. Okay. Yeah, the problem becomes like, is it computationally feasible? Okay.
Right. And okay. So that's of course where we are going.
Just one more quick question.
Sure.
So I'm guessing there's also an extension where the principal doesn't know the cost function for the agent. Is that like a subtype of principal agent problems, or is that an entirely different incentive structure?
Okay. Excellent question. So the question was about what if some aspects of the problem are also private? For example, maybe the cost of the cost of the actions is private, and then we get into a much more complicated model that is combining hidden information, like private information, and hidden action. And this turns out to be a much more complicated problem because we are combining here aspects both of mechanism designing mechanisms that incentivize agents to reveal their cost truthfully, and also engaging in the right actions for the principal. So there are some recent work that combine these two components. It's really just in the very beginning, I think people who are working on contract design are very excited about this direction of combining the two, but we don't know much about it yet.
What should I look up if I want to read more about this?
Okay, let's get to it in the end. Okay, I'll give you some
thanks.
references. Great. Okay. So in this talk, what I'm going to do is I want to focus on two sources of complexity. So of course, this is a TCS talk, so we are going to talk about complex problems computationally. And the two sources of complexity that I'm going to touch upon are multiple agents. So until now, we talked about a very simple model. We had one principal, one agent, and the agent had a list of actions, a set of actions from which he chooses a single action. Now we can think about different sources of complexity. For example, maybe the task is completed not by a single agent, but by a team of agents. That's very common in real life. And then there may be some delicate contingencies, dependencies between the actions taken by different agents. So how do we incentivize a team of agents to engage in some costly effort? And there are many very interesting issues there, for example, free riding. So we'll see all this. The second component, the second source of complexity is the set of actions. So before, we assumed that the agent just takes a single action from a set of actions, but maybe the agent can take any subset of actions. And then again, we have this combinatorial function that maps sets of actions to some, for example, probability of success. So our strategy to study these two sources of complexity for each one of those, in order to understand and isolate the effect of this specific component, we are going to simplify all the other components and really focus, like blow up one component and focus on how it impacts the problem. So we'll start with multiple actions, and this is our Fox 21 paper. So the model is just slightly more complicated than the one I showed you before. We have n actions, 1 to n. The set of actions is A. And now the agent chooses a set of actions. Instead of choosing a single action, the agent chooses a set S of actions. Let's assume that the cost function is additive, namely every action A, small a, has some cost, and the cost of a set of action is just the sum of the individual costs. Okay, very simple. The simplest cost function we can think of, additive. Now here comes the combinatorial complexity. The combinatorial complexity is captured by the function f, the success probability function, which maps sets of actions to a success probability. So every set of actions that the agent may choose is associated with some probability of success, which we denote by f of s. So f of s is the success probability for a set of actions s. And the whole point of this work is that this f is not necessarily additive. Okay, so if it's not additive, one more thing, just like before, the principal's reward is 1 for success and 0 for failure. Okay. So if f is not additive, what is it? And this is where we are using the beautiful hierarchy of valuations introduced to us by Lehman-Nissan. So some of you may be familiar with some of these functions. What I want you to pay attention to here, and we are going to focus on the class of gross substitutes functions. I'm not going to tell you the exact definition of it. It's a bit complicated, and it's not very important that you know precisely the definition. What I want you to know is that it's a strict subset of a very famous class of functions called submodular functions. F is said to be submodular if it has decreasing marginal value. So if you look at the marginal value of an element to a set, it's decreasing as the set increases. Okay, so that's a modular function. So again, gross substitutes functions is a class of functions that is a strict subclass of submodular functions, and it contains very important classes like additive, unidemand. So it's an important class of functions. Okay, good. Now we go back to the previous question. What's the problem we're going to study? So the optimal contract problem can be thought of as a two-stage optimization problem. So the principal wants to find alpha that maximizes her expected utility, namely 1 minus alpha times f of s, right? This is the principal's utility. Subject to what's s? We can think of s as s of alpha. S of alpha, this s is the set that given alpha maximizes the agent's expected utility. Okay, so again, it's a two-stage optimization problem. The principal knows that for every given alpha that she announces, this is the contract is alpha. The agent is going to pick the set of action S that maximizes his expected utility, namely alpha f of s minus c of s. And the problem is find alpha that maximizes 1 minus alpha f of s subject to S maximizing this. Any questions about this? This is the computational problem that we are going to study.
Yeah, one quick question. For cost, you're assuming additive costs throughout the talk?
Yes.
But do you have more general results, or is this kind of where the
okay, good. So for the let me focus now on additive cost and combinatorial success probability. Just like now, F is combinatorial, C is additive. Okay. If I forget, remind me to say a remark about more complicated cost structures. Okay, this is an ongoing work that I'm happy to tell you about. But for now, additive cost. Yes.
Just a quick clarification about this like hierarchical drawing. That refers to the F function or to the C function?
Okay, good. Very, very good. Let's clarify it again. This hierarchy is all about F. F is a function from sets of actions to a success probability. And this F may be additive, maybe gross substitutes, maybe submodular, etc. And C is always additive. Okay, does that answer your question?
Yes, you can't have like a notion of in ordering amongst the set or something like that. Like doing action 1 and then action n or something like that, if it's just additive.
Yeah, only the cost is additive, not F.
Yeah, so you can't have a situation where like doing one thing before the other makes it cheaper or something then.
Not in this model. For now, the cost is additive. Yeah, let's keep it simple for now. Let's just do one component at a time. It's complicated enough this way. Okay, good. So here is the theorem, the main results of this paper. So first of all, we give a polynomial time algorithm for the optimal contract problem for cases where F is gross substitutes. And again, C is additive. C is always additive. Okay. And if we go slightly more general than gross substitutes to submodular functions, then this is the class of functions that exhibits decreasing marginal contribution, then the problem is already NP-hard.
Is it easy to see that such an alpha and S pair would exist? It's
the certain, say it again?
Alpha and S, the pair, it would exist.
Yeah, every alpha induces some set S that maximizes the agent's utility.
Okay, sure, yes.
Okay, good. Now, why are we so excited about this result? So gross substitutes, the class of gross substitutes function is already known to be a frontier, a tractability frontier for different problems, both in economics and in computer science. So it's a very interesting class of functions. First of all, when we are talking about simple resource allocation problem, what we call combinatorial auction, then if we want to maximize the social welfare, gross substitutes function, valuation functions, turns out to be the tractability frontier for this problem. So if agents have gross substitutes valuations, we can maximize social welfare in polynomial time. And in some sense, it's also a frontier. Another problem is completely unrelated, coming from pure economics, market equilibrium existence, not even computational. The existence of market equilibrium, meaning prices that clear the market. So again, if agent valuations are gross substitutes, then we know that a market equilibrium always exists. If we go beyond gross substitutes, in some technical sense, we may not have even the existence of market equilibrium. And now we see a third problem, which is, again, seemingly unrelated to the previous two, coming from CS perspective, computational perspective. And again, we see that the gross substitutes is some sort of a frontier for tractability. And this is for, okay, and we'll soon see what happens and how we are going to use some of the knowledge that we built about gross substitutes functions from previous work. Okay, so before we go to gross substitutes functions, which are very difficult, in order to build intuition, we have a very nice geometric intuition that is based on upper envelope theory. So let's try to have a geometric image of what's going on here. So in this graph, what we are going to have, so first of all, what's the scenario? The scenario is a very simple scenario with 3 actions, 1, 2, and 3. And let's for now assume that both C and F are additive. So the simplest scenario. Every action has a cost, every action has some F, and F of a bundle of actions is just their sum of F, and the cost of a bundle of actions is the sum of their costs. Now, on the x-axis, we have alpha, the contract alpha, and on the y-axis, we have the agent's utility, which, to remind you, is alpha fs minus c of s. Now, we can already observe that for a fixed set of actions S, the agent's utility is just a linear function of alpha. Okay, so for example, for the set of actions 1, 2, we can draw the agent's expected utility. So we see, of course, that if alpha is 0, then the agent has negative utility, incurs cost without getting anything. As alpha increases, the agent's utility increases linearly. At some point, it's better for the agent to take actions 1 and 2 than to not do nothing, right? This is the curve for doing nothing, the empty set. So we see that here, from this point on, it's better to do actions 1 and 2, but maybe doing just action 1 is better than both. For example, in this region, doing action 1 is better than both, and we can draw the linear curves for all sets of actions. And then what governs the agent's actions, the agent's behavior, is the upper envelope of these curves. So essentially what happens is that this upper envelope divides the alpha axis into intervals, and we see what the agent's best response of every interval is. So in this interval, it's best for the agent to do nothing and then do just action 1, then do 1, 2, then do 1, 2, 3. And by the way, this is not a coincidence. So essentially, if f is additive, then it's, if the function f is additive, it's always the case that the agent's best response is always to add 1 more action every transition point. Okay, so we see that the agent starts with nothing, then it adds action 1, then it adds action 2, so it takes 1 and 2, and then 1, 2, 3. Okay, so I didn't prove it to you, but I can tell you that if f is additive, then we have at most n such transitions, where in every transition, the agent just adds 1 more action. Okay, and this is the case for additive f. But now our problem is the principal's problem, which is find the optimal alpha. So let's take now the principal's perspective. So what we see now, again, we see the contract alpha on the x-axis, and what we have on the y-axis is the principal's utility. The principal's utility behaves much less nicely than the agent's utility, which was very continuous and nice. Here, what we do for every interval, for every such interval, the principal knows what the agent, what the set of actions the agent will take. And then within every interval, the set of actions is fixed. So the principal's utility decreases because he's getting the same reward and he's paying more because alpha increases. So obviously, we can already see that the only interesting points are those transition points between points, because within every interval, the principal's utility decreases. Okay, so these are the interesting points, and they're very interesting, so we give them a name. We call them critical alphas. Okay, so those transition points of the agent's best response are what we call critical alphas, and when the principal finds the optimal contract, namely the optimal alpha, the principal can restrict attention only to the set of critical alphas. So now the question is, how do we find the optimal alpha? So this geometric intuition that I showed you suggests a naive algorithm, which is the following. Simply go over all critical alphas, just hop from one critical alpha to another. For every such alpha, compute the principal's utility, and then just take the best one. Okay? Okay. In order for this naive algorithm to work, we need 2 things to work. First of all, for every given alpha, we need to have an algorithm that computes the next critical alpha. Okay, it's not clear that this is doable. Second of all, if we really want naively to hop from one critical alpha to another, and we want a polytime algorithm, it better be the case that we have many critical alphas, critical points. So for additive f, I already told you that this is the case. We only have a linear number of transitions because every time we just add one action because of the nice and very independent structure of additive f. But for gross substitutes or more combinatorial functions, this is not the case. However, we show that this naive algorithm yields a polynomial time algorithm as long as f is gross substitutes. Okay, so essentially what I need to show you is 2 things. First of all, that we can, given some alpha, for a gross substitutes f, we can compute the next critical alpha in polynomial time. And second, that we have many critical points. And actually, one more thing is that we can compute the agent's best response in polynomial time. Okay, now even that is not clear. Good. So this is the case for gross substitutes. By the way, as a remark, this is no longer true for submodular functions, which may admit exponentially many critical alphas. So in fact, we can build a submodular function that spans the entire collection of sets. So it has 2 to the n possible critical points. So the agent's best response spans the entire collection of subsets. Okay, good.
I have a question.
Yes.
If you go back to the previous slide, you commented that if you have submodular function f, then the number of critical alphas is exponentially many. Can you still find the next critical alpha in poly time?
Okay, great question. The answer, okay, so let me tell you 2 things. First of all, I can find the next critical alpha in poly time. Second of all, this in itself, the fact that we have exponentially many critical alphas in itself does not mean that the problem is hard. All it means is that this approach would fail to give a polytime algorithm. But other than this result, we also show NP hardness for some modular functions.
Okay, but it seems the NP hardness is not coming from finding the next critical alpha.
Correct. Right? Next critical alpha is easy.
Okay.
So if I understand, the next critical alpha would be adding finding which one more action to add, and would be one set, like the cardinality would be one higher, right? Even for agent.
Sorry, say it again, please.
The cardinality of the set of actions S would be one higher, but we don't know which action to add. So
no. So no? For additive, if F is additive, then you are right. We can only add one more action. For more general functions of F, we don't know that. It may go crazy. For example, for submodular, it may change. It goes, up and down, and it spans the entire space.
Okay. Thank you.
Okay, good. And okay, good. So your question is really good in directing me to the next slide, which is how does the transition of best response look, for example, for gross substitutes function? So this is an example. So I don't show you here the exact gross substitutes function, but believe me that this is a real drawing of some transitions for some gross substitutes function. So let's look at the transitions. It's very interesting. So this is the upper envelope. Again, 3 actions, some gross substitutes function F and additive function C. And what we see is that the agent's best response is the following. It starts with empty set, then it adds the action 1. Then, and this is related to your question, it doesn't add action 2 to 1. It replaces action 1 by action 2. Okay, so the cardinality doesn't increase, but it just replaces one action by another. Then adding action 1 again. So look here, it's not monotone. Like we dropped action 1, then we added action 1, and then we are adding action 3. So a bit crazy, but not too crazy, right? Okay. So now let's take a closer look. So first of all, let's look at the agent's problem.
A question from the audience. I guess you're trying to not give the explicit definition of gross substitute valuation, right?
Yeah. After the talk, I'm happy to give it. Okay. It will take too much time. Okay. Good. So let's take a closer look at the agent's problem. The agent's problem is the following. Given alpha, so fix alpha, because the principal announces alpha, find the set S that maximizes alpha Fs minus C of S, right? And let me remind you, C of S is additive, F of S is gross substitutes, okay? Now, okay, it's not coming as a surprise to you that this problem is equivalent to maximizing F of S minus 1 over alpha CS, of course, we just divided by alpha. Okay, and now this structure should ring a bell. Those of you who worked on combinatorial actions and demand queries, it rings a bell, because this is precisely maximizing this S is precisely solving a demand set with prices C over alpha. Okay, C is additive. So, okay, let me tell you what, and this is in markets for goods. So let me very fast tell you what a demand set is. So a demand set, so think about an agent, and the agent has valuation function F, mapping sets of items to values, and item prices P that are additive. So the demand set of an agent is a set S. Let's forget about ties now. A set S maximizing the utility of the agent that is defined to be f of S minus the sum of item prices. Okay, this is a demand set. A key property of gross substitutes function, and this is the really nice thing about gross substitutes function, is that greedy algorithm solves the demand set problem. Namely, what do we mean by a greedy algorithm? Simply every iteration just adds the element with the maximal marginal utility. So every item increases F in some way, but also adds some price, some cost. So just add the one item that maximizes the marginal utility, as long as the marginal utility is greater or equal than zero, and then stop. This greedy algorithm solves the demand set problem for gross substitutes function, which is really nice. So we have a polytime algorithm for the agent's best response because those two problems are precisely equivalent. For more general functions, like for submodular functions, solving a demand set is already NP-hard. Okay, so this is really a nice thing about gross substitutes function. Let's forget about tie breaking for now because I'm almost running out of time. Okay, good. So with this in mind, okay, I told you next critical alpha. Let's skip this slide. It's not very interesting. It's a relatively easy problem. The more interesting thing is to show that we have many critical alphas. Okay, good. So we already showed that we are losing, moving from an additive F to a gross substitutes F, we are losing the nice, very nice, simple structure of heading one action at a time. However, what we can show, and this is really the key lemma that facilitates our results for gross substitutes function, is that at each critical point, only one of two things can happen. Either an action is added to S, just like in additive F, just like we see, for example, here, moving from action 2 to the set 1, 2, or an action from S may be replaced by one with higher cost. And this is what's happening here. The action 1, which is less costly, is replaced with an action 2 that is more costly. And these are the only two things that can happen. And this is really the key lemma that we are using. So we see that the structure is more complicated than additive, but not much more complicated. And then using a very simple potential function argument, we can complete the argument to conclude that we can only have at most n squared critical points for gross substitutes. And then the algorithm just follows because we can compute next critical alpha in polynomial time. We can compute the agent's best response in polynomial time. This is simply a demand query, and we know greedy works. And we show here, using a potential function argument and the key observation here, that we can only have at most a quadratic number of critical points. Okay, so we are done for gross substitutes. Great. So the main takeaways from this part of the talk, and I see now that I'm almost running out of time, so the next part I'll just give you really a gist of it. The main takeaway here is that, again, in at least two other very crucial and fundamental problems, both in computer science and in economics, gross substitutes exhibits some frontier of tractability. And this is for an entirely new problem, combinatorial contracts. Okay, and we see some surprising connection to auctions. Let me skip the other parts and say just, so David, how much time do I have?
Definitely take another, say, 15 minutes. Then we'll open the floor for questions.
Okay, you said 15, 1-5.
1-5, yes.
Yeah, not 5-0. Good. Okay, so let me tell you a bit about multiple agents. So again, this is very simple model to before with a slight complication. And now the complication comes from the number of agents. So now we have n agents. As I said before, we complicate one thing. We have a team of agents. So let's simplify the other things. Every agent has just a binary action, either exert effort or not. So AI is the set of actions of agent I. No effort, 0, effort is 1. The cost of effort for agent I is CI, and it's 0 for no effort. And again, like before, we have a binary outcome, 0 or 1. The project either succeeds or not, and the principal receives a reward of 1 for success project. Okay, so very similar model to before, except now we really simplify the actions. Every agent has a single action, but we complicated the teamwork. We have n agents, and where does that complexity emerge? Again, it emerges in the function f that now maps the decisions, the binary decisions of the n agents into a success probability. Okay, so for every subset of agents that exert effort, we have some probability of success. And again, this function can be combinatorial, and that's where the interesting stuff comes in. Okay, good. So now the optimal contract is given by a vector of alpha, unlike before where the contract was just with one agent. Now it's with n agents. So every agent I is presented some alpha I, which is how much that agent is paid in the event that the project succeeds. Okay, so a contract is given by a vector of alpha, where alpha I is non-negative, and it's the payment that goes to the agent I if the project succeeds. So let's again take the agent's perspective. So let's fix the behavior of all other agents. When does agent I prefer to exert effort than to shirk? So agent I prefers effort over no effort if and only if the agent's utility for effort, which is alpha I fs minus ci, is greater than agent's I utility under no effort. What's the agent's utility under no effort? So now the agent receives alpha I with a smaller probability. So before the agent received alpha I with probability f of s, now the agent receives alpha I only with probability f of s minus I. What's the trade-off? The trade-off is that if the agent exerts utility, and exerts effort, then it also incurs the cost of CI. Whereas if it doesn't exert effort, the cost disappears. Okay, good. So this is the agent's perspective, and with this we get that the best way, fixing the behavior of all other agents, the best way to get I to exert effort, to incentivize I to exert effort, is to propose to him an alpha I that balances these two terms, namely alpha I equals CI over the marginal contribution of I to F, okay, given S minus A. Good. This is just by equating these two utilities. Okay.
I have a question.
Sure.
So can you clarify a bit more what this notation is? F of I given S minus I?
Yeah, okay, good. So here is f of I given s minus I is just it's the marginal contribution of I to s minus I, namely, is the difference between f of s and f of s minus I. Okay, how much the fact that A exerts effort, how much does it add to the probability of success?
Sorry, I also have a question. For which S should this hold? Should it hold only for the S that's in the equilibrium, or should it hold for all?
Exactly. Exactly. Great question. So now when we are talking about team project, we are talking about equilibrium. And we are going to take the equilibrium notion.
Okay, thank you.
Okay, so S is an equilibrium if every agent prefers effort to no effort in S, given S. Okay, so now let's take the principal's perspective. The principal's perspective is to find the set of agent S that maximizes the principal's utility. Let's call it G of S here. What's G of S? It's F of S. So remember, before it was F of S times 1 minus alpha. Now it's 1 minus the sum of alpha I. And every alpha I is just Ci over the marginal contribution. Okay, so this is the principal's objective. And again, the problem is compute the optimal contract for interesting functions of F, for example, for submodular F, or for XOS F, or for subadditive F. Okay, and these are classes from the hierarchy of valuations that we know. Okay, now the challenge is the following. So let's take a look. This is the objective function of the principal, this G of S. The challenge stems from the fact that even if S is highly structured, for example, maybe it's submodular or XOS, G is highly non-structured. For example, here you can see two examples. You can see an additive, very nicely behaving function F that is additive, and look at G. G may be non-monotone, it may be negative, quite crazy. And here is another example. Here is an F that is XOS, so nice function, XOS. And here G may really go crazy. It may be non-monotone, even non-subadditive, and again, non-positive, like negative. So maximizing G is very challenging. Okay, by the way, for those of you who are not, who don't know the definitions, subadditive is this very large class of function, and all it means is that it's also called complement free. It means that the sum of F of two sets is always greater than F of their union. Okay, and it's known to be a superclass of submodular, and XOS is something in between. Let's not go into the definition. Okay, let me skip this slide. This is a kind of a motivating slide, but I don't have time for this. I want to present the main results. So first of all, the main positive result, which is also the main result of this work, is that we have a polytime algorithm for finding constant approximation for the optimal contract for the case where F is submodular or XOS. Now, for F that is submodular, we can have constant approximation using just value queries, which are weaker. And for XOS function, we get this result with access to demand queries, which are stronger. Okay, so what's value query? A value query is given S, return F of S. Okay, because remember, F is this combinatorial function, so it's exponential, it's an exponential object. How do we even access it? So two very common Oracle models are value Oracle, which is given as return F of S, and demand Oracle, which is again just the demand query that I told you about before. Given action prices, P1 to Pn, return the set S, maximizing F of S minus the sum of prices. Okay, and so with these oracles, we can get constant approximation to the optimal contract problem. If we go slightly above XOS functions to a subadditive function, then we cannot get constant approximation. In fact, we cannot get better than omega root n approximation for the optimal contract problem. Okay, You may wonder, why do I go to approximation? What about maybe optimal contract? Well, even for additive F, this problem is NP hard. Okay, I already have it. So for additive, it is NP hard to find the optimal contract, but we have an FP task. And constant approximation is all we can hope for XOS functions. Okay, so these are the two main results. I am going to skip the proof sketch because I'm running out of time. Let me just maybe highlight a few points about this proof. So the first point that, I don't expect you to follow this slide, just 2 points. One is that we are using here a very non-standard, we have a non-standard use of demand queries here. So we want to find a set that maximizes the optimal contract, and we are issuing demand queries in a very non-standard way. So I'm not going to give you more details about it, just the demand queries may be more useful than we thought they were. So the standard way of using them is like in combinatorial auctions. We want to find the agent's best bundle under some prices, and here we are using it in a very different way. So this is one thing. Another thing is that I already told you that submodular functions is the class of functions that exhibits decreasing marginal value, meaning that as we increase the set S, the marginal value with respect to S decreases, okay? In order for our proof for XOS functions to work, we need to keep the marginal, we need some lower bounds on our marginal values. Okay, so you see here that we want the marginal value to be high enough. The problem is that the set, the set we begin with may be too large. So if F was submodular, we could just start decreasing, like removing actions, removing elements from this set T that we begin with. And if F is submodular, then the marginal value can only increase because we remove items. So the marginal contribution of the existing items can only increase, which is good for us. But with XOS, we lose control of marginal contribution because we don't have the very nice property of decreasing marginal contribution. What we use in order to have this result is a very nice new scaling property of XOS, meaning that we can still scale down f of t. So starting with some set t, we can scale down f of t by removing some items from it, because we need f of t to be a bit smaller, and still keep the marginals high enough. So in a sense, we have a new algorithm that we construct that controls the marginal contribution of items, even if the function is beyond submodular, even if it's XOS. Okay, so we scale down. So we start with some set t, we scale down ft by removing some items cleverly and keeping the marginal contribution of the remaining items high enough. I mean, not high as below, but as before, but sufficiently high. Okay, and so this is another nice new thing about XOS functions that facilitates our result. And with this, I think I'm going to skip directly to the summary. So I hope I convinced you by now that contract theory is a very exciting new frontier in algorithmic game theory, and that taking the computational and algorithmic lens toward studying it is very interesting, and it sheds new light on like the structure and the tractability of contract design. There are very interesting connections to combinatorial auctions, I didn't tell you everything, but I hinted on some. For example, the fact that cross substitutes is a frontier, is a tractability frontier. Although there are some very interesting differences between combinatorial auctions and combinatorial contracts. And I think maybe the most important thing is that there are many fundamental open problems. So I think it's a very nice area to look for open problems. And with this, I'm going to conclude, and thank you all for listening.
Thank you very much, Michal, for I imagine putting in some effort, because there's definitely some nice reward from this talk.
Well, you paid me well.
Right, so I guess I'll open the floor up for questions now. Actually, let me maybe pause the recording, and we can make things more comfortable for people to ask questions.
Okay, let me try to move the